Hello, hello. I think I'm live. It says you're live. If someone can say something. I don't see myself live in the other window. That's not a good sign. Am I live in the wrong place? I should be live. What's happening? Oh yeah, I am live. All right. Up. Hello, hello. I'm gonna wait a few minutes. Just make sure that people have time to join if there's more people. Um, good morning or good night. I don't know where you folks are joining from. Cool. Yeah, I'll try and monitor the chat, so don't hesitate to ask questions as I do this. I'm basically hoping to attract new contributors, so I'm happy to answer all sorts of questions and dig into things as we go. I wish I could put some music, like a wedding music. Let me do one last tweet about this. All right, so I guess, all right, let's wait one more minute and let's get started. Is this recorded? I think it's recorded by default and I can make it available at the end. But this is the first time I'm doing this. So to be honest, I don't know, but this is YouTube after all. So it should be recorded. All right. Let's get started then. So I guess I should share. If you don't know, maybe I'll share the project first. Oops. All right, how do I share? So if you don't know the project, this is the project. I'm assuming most people here might have heard about it and glanced at the GitHub at the very least. But basically, it's an open source project that we're developing at ZK Security. We have a grant from the Ethereum Foundation to work on that as well. And it's a pretty small grant to sort of help us get this off the ground. So we're really looking for contributors and people to help us. And I think the greatness of this language could really come from the community more than like a few people here. And so anyway, you can, if you want there today, you can clone the repo, or you can just type that command. It's a Rust. It's made in Rust, so you have to use cargo to install it. We don't really have binaries, or we don't have a good CI to produce releases yet. So this is kind of what we have. And then after, what you get is this CLI. And this CLI is basically like cargo. You can create new projects. You'll get a TOML file, kind of like cargo, a source directory with your file, and as you look at the code, you'll see that it's quite inspired by Rust. Here you have a pretty simple example, and I'll go over more examples, but just as a glance, you can see it's very Rust inspired, and so that's good to know. The other thing is that it's also very Golang inspired, and so if you like Go, you might recognize a number of design decisions that come from that, including how the package manager works for now. We have like a sort of a poor man's package manager, where you just push stuff on GitHub, and you can just point to a GitHub and it'll just get the code that's there. There's no versioning, kind of like the early days of Golang, and it's, it just works. It's not perfect, but it's a good way to share code, and at least we have that. The other thing I should mention, we have a book here that should be a pretty good resource if you're trying to learn the language, or like how the inners work. It's not the most up-to-date book, but a lot of things should be quite up-to-date. We just haven't updated it in the last changes that we've made. Yeah, you can understand how different concepts in the like, if you don't understand some concept, you can search for it here, and it might show up here. So we explain vars and how constants work, and the type checker, and so on. And of course, contributions are welcome. If something's missing or not up to date, tell us, or create a PR. Cool. What else can I say before I start digging into the code? And again, if you have questions, I'm monitoring the chat, so ask me there. But this is pretty much it. I can also tell you about the state of things as of now. The state is that, so noname used to be a language, programming language to write circuits for Kimchi. Kimchi is a Plonk proof system that was developed at O1 Labs for Mina, and so the whole idea was to make it work for Kimchi specifically, but we changed that, and a lot of the work we've done recently in the last months was to make it work for R1CS, and to make it compatible with Snark.js, which is the tool that most people use to deploy smart contracts, to deploy zero-knowledge proof verifiers directly on Ethereum. And so we wanted people to use this easily with whatever stack they were familiar with. And so today, if you want to, we actually have a blog post somewhere. That's not this blog post. Maybe we should link to that blog post here. But we have a blog post on the ZK Security blog where we explain how to deploy a noname program on Ethereum, and we also give you an example. So there's one on the testnet that you can use, and and last thing I'll say about the state is that it's not in the best state ever. It's not something that you can really use today to write cool applications that could replace Circom or Gnark or other Socrates or other DSLs or EDSLs that you have right now. It's very much a work in progress, and so there's a lot of things that are not implemented, and there's actually a lot of low-hanging fruits and like very easy things to implement. I don't even remember if like some arithmetic operations if all arithmetic operations are implemented on fields. So one thing that I would recommend if you want to contribute is to write code. So look at the examples. All the examples are tested and should run. They're here, and maybe we can go over some of them. Look at the examples and then try to write your own stuff. And if it doesn't compile, if your stuff doesn't work, then maybe submit an issue or maybe even work on it to make it work. And I'll show you how you can do that. Okay, so Logan had a question. What are the end goals of noname? Is it transitioning to be a language for proofs on Ethereum, general ZK computation? So the main goal right now is to make it usable for you to write interesting applications on Ethereum. We're targeting Ethereum specifically because this is where a lot of people are using Circom and these kind of languages that are more like low level. And we wanted to offer like a more high level language which you can use to create, nice abstractions and so on. Like Circom is a very like circuit level language, and so we wanted something else that was not a embedded DSL and that was more like a language like Rust or Golang, which are languages that we like. That being said, you don't have to use it on Ethereum. Whatever chain, it's really it's sort of an agnostic language, and that's what I'll try to explain. There's this notion of backends, and you can just write programs and run them, and then you can decide what to compile them to. And for now, we support R1CS or the Snark.js version of R1CS to make it easy to use it with Snark.js, or we support Kimchi. But if these don't work for you or are not supported in whatever environment you're in, you could try to implement a different target or backend and make it work there. We're actually working on implementing 2 other backends, Sonobe, which allows us to do folding of proofs with Nova. And we're also looking at Circe, which will allow us to do formal verification and different things on the circuits that we write. Where do you place noname between NARC, SP1? So SP1, if I remember correctly, is a ZKVM. And so noname is really like you're writing code that will compile directly to a circuit. And so in this sense, it's supposed to be much more performance. Like you have access to much more low level like things, but it's not a ZKVM, so it's less easy to use. There's things that you don't have access to that maybe we could try to emulate, but that would be harder to emulate because we're writing circuits directly. So notably, when you're writing circuits directly, doing like large if else or like branching is hard, jumping around is hard, early return is hard, dynamic loops is hard, or breaking from a loop. But all of these things can be sort of emulated, but it's hard, and so we don't really have them in noname, and this is something we're trying to bring. Gnark is more similar to what Circom is. I'd say it's a more lower level language that's closer to the circuit than we are. So think of noname as a higher level language with types, and it's a DSL also. Gnark is an embedded DSL. And so it's sort of a different beast of its own. I would say it's, so yeah, thanks for bringing up Noir. I would say it's more comparable to Noir. Or who else would be? I think Noir would be the better comparison. I'm not sure who else is in this. Trying to think, yeah. If you think about it and you write it, I'll say it. But Noir is the more direct. Let's not competitor because they're focusing more on Aztec network, and while we're trying to like just make it useful for Ethereum or different networks. So that I would say that's the difference. How difficult would it be to prove these things in Coq? So we're looking to I'm not really a formal verification person, so it's hard to answer, but we're looking to integrate that with CRC, which will allow us to basically use SMT solvers and do more interesting things. But this is pretty early. Actually, we have a call next week to talk about that and the integration. So maybe I'll have some news to write about that in like a few weeks. Yeah, I don't know about lurk specifically. I think it's I mean, it seems like it's more like a zkVM, but I'm not super familiar with the project. All right, so yeah, I guess the last question, maybe I'll look at the last question, but maybe it's time I dig into the code and I show you more stuff. But you're asking, can you have logic branches if else in IVC proof system? IVC is just orthogonal to that. You can try to create if else branches in whatever circuits, and an IVC proof system is just a collection of circuits or the same circuit repeated over and over. So let's say it's orthogonal. Cool. So okay, let's look at some examples. I believe you can see my screen and it should be large enough. So the examples directory has some examples. You can go over them. Actually, I'll do that from the editor for now. And you'll see a number of .no file. Actually, somebody asked me about the noname name. Noname was really a placeholder because I didn't want to think about a name, and I just wanted to start working on that project. That was like a while ago, and so we never really changed that. If someone has a good idea of a name, maybe we should change the name. But it's called noname for now. The files are called .no, and it is what it is. Okay, so arithmetic is the simplest example we have. Noname is a good name. That sounds good. Someone told us about kombucha also, which was a good name. We just never changed the name, I guess. So anyway, when you write a circuit, you write a main function. So it looks like Rust. And you take arguments, which are going to be your inputs. And you can see that one of the argument has a public modifier. And so no, it's not like you have to know about proof system, but if you know about proof system, you can just guess this is a public input, and this doesn't have a public modifier, so it's a private input. But these are just the names. They could be anything. What matters is that pub keyword. And if you don't know how zero-knowledge proof systems work, just think about it this way. This input will be known to the verifier who verifies this the execution of that function, but this will be hidden. And then what's the logic? Well, these are field types, and field types are basically the unit types of our system. This is the native type, sort of like I guess a usize is the native type. Would be the native type like in like a low-level system language. For us, it's field, and then every other type is built around this field, right? It's like a register, I guess. And you'll see we have like a Boolean type also, but we don't really have other types as for now. But if we had a uint8 type or uint32 type, we would build them based on this field type. And so this field type has supposedly all of the arithmetic operations built on it, from addition, multiplication, division, and all of these things. As I said earlier, some of these things might be missing. So lots of low-hanging fruits that might be easier task to start contributing. And the way you sort of do interesting thing in a circuit is that you call this assert function. And here I mean, this example is pretty self-explanatory. Can you choose which field you're working on? For now, there's only one field. I guess the scalar field of BN254, because that's what Ethereum uses for the most part. But it's not hard to, the code changes wouldn't be hard to do to support different fields or different. Basically, we're talking about curves. It's just a matter of creating a new backend, and it's, if someone asked for like a new curve, we can add it. But the work is pretty minimal usually. It's just about creating a different backend. All right, so yeah, going through them maybe quickly. We support arrays, so you can pass these types. It looks like Rust again, and you can create arrays this way, and you can assert equality between. I guess you can do indexing of arrays. I mean, you know, what you would expect from like these kind of languages. You can create your own structs with their fields. You can you can take these structs as arguments of your function. We don't support that as argument of the main function yet. It's not like it's complicated. It's just that we haven't written the code. I guess it's another low-hanging fruit. You can instantiate your custom structure, access fields of your custom structures, and so on. I don't remember if you can call assert equal on structures, but if it doesn't work, that's something we should implement. Boolean. So yeah, you can take Boolean as well. You can use this AND operator. I think this is the only operator that works, but again, low-hanging fruits, if someone wants to implement the or XOR or these kind of things, they're pretty straightforward to implement. And you can assert based on these booleans with the not operator. We have constants if you want to use constants in your circuits. Equal, I guess the equality sign. All of these things are, you know, they seem like the kind of things you would expect from from this kind of language, but you know, whatever. For loops, the for loops, as I said earlier, we're not a zkVM, so the loops have to be static. Have to be of constant number of iteration, and so this is what we do. We can range. You can create functions. So the if and else only works for more like a ternary operator. You can't have like actual blocks in them. This is something we're investigating how to implement that, but for now you can only do that for assigning the value of a new variable to either one or the other. I guess this example is a bit more complicated, but here you can sort of see again another custom structure. But what's interesting maybe is the syntax for implementation or method on that structure that looks more like Golang than Rust. So this is how you write the implementation of the method room on the house struct. The only reason we went this way is that like in Rust, if you have these big blocks like of implementation and like a ton of functions, or implementation house and a ton of function, then it's sort of hard to know which what you're implementing a method on. So we just chose a different syntax, but it's basically the same. And here it says it's an iterate example. So where do we iterate? Yeah, I guess we just do a range. So that's not really an iteration. But anyway, what's interesting here? Oh, we can have library. I explained that at the beginning. If you're not here, if you push code to like a repository, let's say user repo on GitHub, you can basically list dependencies in the noname.toml file, like in Rust. And if you list that dependency, noname will directly fetch that code on the repo and check if there's a noname file. And if there's a noname file, it's a library, there's no main function, you will be able to use that code. And the way you can use that code, I don't have an example here. I should have an example, but it's very Rust/Golang style, where you would do user repo in your code. You would write it like that, and then you would do repo my function or my constant and these kind of things. So you always have to qualify it, and that's you always know that something comes from that library. So anyway, okay, let's go quickly over the rest, and then I'll dig into the code, which I think is more interesting. And but just to give you an idea of methods, I've already showed you that. We have a mutable keyword also. You're not supposed to mutate something if it's not mutable. So very much like Rust. Poseidon only works for Kimchi. We don't have an implementation for R1CS. Oh, we have output, of course. So if the main function returns something, like in Rust, then this will be a public output. We don't have private outputs. I don't know if that would make sense to have, but you can return stuff like that. Static methods, I don't know why I call that static methods. Huh. We have a Sudoku example. I think this is probably the most complex example we have. So if you want to see like more like, if you want to see all of the stuff that we have, basically this probably uses all of it. And anything that looks ugly, it's because we don't have something to write it more nicely. Yeah, this is arrays and custom types. Okay, so yeah, let's dig into the code. I think there was maybe one. Oh yeah, there's also maybe one particularity. I don't need to explain it, but maybe it's interesting to mention it. But you have a const keyword. Some function can take arguments that are const, and basically this is sort of required to warn the caller that this is gonna have to be a constant and cannot be a field element. Yeah, function outputs are always public. Hey, Vivo. All right, so let's dig into some code. Unless people have questions here that were more high level. Otherwise, I can try and dig into the code and explain how the internals work. I'm going to share my other window. Okay, so you should see my code now. Hopefully it's not too tiny. I think it's visible. Oh, function outputs are not public outputs. I mean, the main, if you have an output for the main function, then that output is public, but any other function, it has automatically a private output, right? So everything's private, except the output of the main function or argument of the main function that are marked as public. All right, so let's look at the code. So we have the book, which is the documentation that I showed earlier. So check the book. We have examples, which are, oh, one thing to maybe I'll run some example, and then I'll show you what's cool with noname. Maybe I should have started with that. Okay, so I'll cargo run. So I'm gonna run the arithmetic example. All right, I'm gonna run that. Oh, one sec. I'm gonna run that and show you why it's a cool programming language that we created here. Okay, lots of errors, but that's okay. Okay, so I run this example, and I run it with the debug arguments. And you can see how I run it. I just gave it a path with a test. Test is something that creates a compile it, creates a proof, runs it, does everything basically to test the whole gamut. Actually, for R1CS, it doesn't create a proof, but for Kimchi, it does create a proof. And here you pass a private input and a public input. The private input is the name of the argument. This is the name of the argument. Yeah, if I pass the wrong inputs here, the assert equal is not going to work, but here I'm passing the correct one. And the debug stuff is interesting. Oh, and these are JSON. The format expected is JSON. And the debug stuff here is basically something that tells you how it compiles down to R1CS or Plonk gates if you're looking at Plonk. So if you look at R1CS, you can see that it created these constraints. And you can see why it created this constraint because of this file and this line of code. And then you can see basically there are two constraints, and you can see why these two constraints are created. And so you can sort of guess which variables are assigned to what variable in the code. And maybe I can try to pass the backend Kimchi. Is it called Kimchi Vesta? Hey, what? Oh. Okay, so if you want to compile with Kimchi, it will create a proof and verify it, show you the witness, and also show you why it creates every gate. Here we have an indication of exactly why actually. So I guess we should add that in our R1CS. And you can also see the wiring because in Plonk you have to do some wiring. So all of these things are wired together. You can see the wiring. So depending on the backend you choose, you have a different type of debugging information. Yeah, so we have a blog post. If you go on the ZK Security, Vuvo, if you go on the ZK Security blog, I think one of the last blog posts is on noname, and we showcase an example of a Sudoku solver that's deployed on the testnet of Ethereum and how you can do it yourself. Why there are two constraints here instead of just one? Let's so Baptiste is asking why there are two constraints. I mean, maybe you could have created something with only one constraint if you can optimize this out. And maybe that's an optimization we're not doing. But basically, this is with the optimizations that we have today, this is the minimum amount of constraints that we managed to create. The reason is, and this will become more apparent maybe if I go through the code, but a multiplication always triggers constraints. And this is not because it has to, but because this is the way this is as far as we optimize things. So additions in our R1CS will sort of like continue creating a linear combination. But when you have a multiplication where like we just give up on accumulating things in a linear combination and we just create a constraint to sort of reduce that to a variable. And same thing for assert functions. Or in this cat in the chat is another core developer, noname, so I guess he can answer questions there as well. Okay, so let's look at the code, and you can see that if you go in fixture and in Kimchi or R1CS, you can also see all of the compilation of the examples that we have, which is quite handy. When we make changes, we can see exactly what changes in the constraints. We can find bugs this way. We can really review things quite nicely. And same in Kimchi, we have the different. These are like pure circuits, basically. Okay, and so in the source, we have basically the different elements of the compilation to sort of explain how things work, especially if you don't know compilers. Usually you give a bunch of files to a compiler, and the compiler takes these files, like these node files, and then give them to the lexer. So we have the lexer here. And the lexer basically is very dumb. It's pretty minimal code, and it just spits out token, what they call tokens, and these tokens are basically fn main parentheses keyword pub identifier public input colon keyword field comma identifier private input, and it just spits out a bunch of stuff. It doesn't understand anything, but it gives you something that's nicer to use. After the lexer, you have the parser, and the parser basically will go through that and create something that has more sense. And it will create that. Lexer creates. Maybe I'll write that. It sends tokens to the parser. The parser creates an AST. And we can go in the parser. Here, actually, we can go in the lexer. We can see that we have a token type, and a token type is basically a token kind and a span, and that's the token kind is what I was talking about. It spits out a bunch of these things, like a long list of these things. So here, parentheses, left parentheses, right parentheses, and so on. Maybe something that's good to mention, but whenever we have something, an object in noname, we often have a span that accompanies it. It's a very common thing to have in a compiler. A span just tells you what file it was in, where in the file it starts, and for how long it goes. And this is very useful for debugging. So whenever you see a span, that's for debugging. Okay, so let's look at the parser, and you'll see the same stuff. You have a main parse function, and it returns. Oh, sorry, that's not the main parse function. What am I saying? All of these blocks that creates the compiler should have a main function called parse or something like that. That basically returns the next step, the next phase of compilation. And we could actually just debug things. Maybe let's get into debugging to sort of show that. Or actually, no, not yet. Give me a few more seconds. You can see that parse create an AST, and it takes a bunch of tokens. So the output of the lexer, and you can look at the AST, and it's an AST is a list of roots, and a root is again a span. It's either a use statement to import something, the definition of a function, a comment, the definition of a struct, or a constant. A constant. I'm talking about this constant here. And then if you go in the function definition, you can see it has a signature, a body. A body is a bunch of statements, and statements are like assignments, expression, a return, a for loop, and you can look. You can just can make your way if you don't know what the AST looks like, and sort of click through things, and you can see, okay, an expression is a function call, or a method call, or another assignment, or a field access, and so on. So this is really why it's called a tree, because if you look at it, it's sort of it's boxes into boxes into boxes, and this is how we represent the code, and this is the main, one of the most important compilation phase. This is the lexer and the parser are pretty stable because the language is things compile, and most of what's missing is right now in the gadgets, in the circuitry, in the transition from code to circuits. Okay, so what happens after the parser? We send some AST to the type checker. And we have a type checker because we're a type language, right? If you look at our examples, we have types here, like in Rust. And so we need to have a type checking compilation phase, which is in the type checker folder. Everything is pretty organized. And here you should have another function that's another main function that takes the output of the parser and creates what we call typed AST. For AST is abstract syntax tree, doesn't really matter. But yeah. typed AST. So where's the main function? New analyze. I guess it's called analyze here. And oh, it takes an NAST. Okay, I did forget one phase. Before we send it to the type checker, we have the name resolution phase, which return an NAST. Oops, it's gonna be earlier. So we're not at the type checker yet. We actually do a name resolution phase. The name resolution phase is basically because we deal with modules and libraries, and if in your noname code, in your noname code, sometimes you call functions, and you need to make sure that these functions are the right functions. They could be local functions, or they could be function of a different library. And so name resolution basically tells us for every function and variable and constants and whatever, where it comes from. That's what name resolution does. And so you can see the NAST. If you look at the NAST type, it's still just an AST. Nothing has changed, but I think some of the things in the ST have been populated. They were options, and they were none, and they became set to something. Hopefully that makes sense. I don't want to spend too much time explaining things at the high level, and I want to get to like actually stepping through the program just to show you how it compiles things. Okay, after the type checker, basically that's when we decide to do the circuit compilation. And this will produce a compiled circuit. And that is, a pretty important phase of the compilation. And so that is in constraints. In constraints, we have, oh no, it's not in constraints. It's in circuit writer. In circuit writer, we have, again, a function that should be the main function, generate circuit. And the generate circuit takes the output of the type checker, a backend. So this is where we decide if we want to compile to R1CS or Kimchi for the Plonk case, and then we create the circuits. And you can see a compiled circuit is, okay, I'm not going to show you what it is, but there's a compiled circuits. And maybe one last thing I can mention. Okay, I'll look at questions, and then I'll mention two other things. I should probably mention witness generation and the backend. Like what do backends look like? And then I'll go into debugging. Okay, so it seems like Park Marco could have gone crazy here. Yeah. All right. No questions. Okay, I guess I'll finish the overview before I start debugging things. But as we create these compiled circuits, basically we go through the AST or the typed AST, like the final AST. And by looking at it, we decide to create constraints and to add things in the witness. We create constraints, meaning we, for R1CS, we populate these matrices, for example. But when we fill the witness, we fill it not with real witness values, because at this stage, we're not running a proof. We fill them with symbolic witness values. And symbolic witness values are basically instructions and recipes on how to compute these witness values at runtime. Like once you want to create a proof, you can look at these instructions and they'll tell you exactly how to create a proof. And so if you look at the witness generation, which is what you use when you want to create a proof, we should be in I guess we don't have a folder for that, it should be in witness. You will see that it's basically an interpreter that goes through a list of instructions that we sort of left there when we compiled the circuits. We just created these instructions when we compiled the circuits, and we're just going over there in this witness generation. What this means is that if you want to create a proof, or if you want to create a witness, the first thing you'll do is run that witness generation. And this is Mary here that made a cameo. But if you want to create a witness generation, you can do it either by running noname, or you can do it by writing your own interpreter in a different language if you want, or you can do it by compiling these to WASM and running that if you want, you know, whatever you want to do. Okay, so that's the witness generation part. I'll look at the backend stuff, but if you have questions, please ask them, and because then I guess we'll change gears. Okay, let's just look at briefly what a backend is. We have Kimchi, Vesta, so it's Kimchi for the Vesta curve. R1CS for, I guess we support 2 curves, but this is the main curve we're trying to support. And if you want to add a new backend, you basically have to implement that trait. And a backend basically has a specific field, the field that you use in your circuits. It has the notion of variables. Basically, you can think of a variable as you can almost think about it as a cell in the witness table. But it's a symbolic cell, so it might not have become a cell yet. As we want to create optimization, where maybe we're deferring the creation of a witness cell, and so there's that type for like what does a witness look like, and then like in each circuit function, there's a finalist circuit function. There's a bunch of functions like how do you add variables together, how do you subtract variables together, and so on. How do you add a public input? How do you add a private input? And how do you compute a variable at runtime when you're really trying to create a proof? But yeah, these are all pretty basic. And if you look at the examples of R1CS or Kimchi, you can see how we did that. But it's not too hard, I guess. Okay, so let's dig into the debugging of things. I think that's interesting, and it can sort of show how things work. But yeah, does that make sense? Is that do you guys have any questions on what I've said so far? So you can really think that we're agnostic to, yeah, you're asking if we're outputting a prover key and a verifier key, but we're really agnostic to that. The only thing we create is an arithmetization and a symbolic witness, and the symbolic witness can be used by whoever wants to create a witness, and the circuit can be used by whoever wants to create a prover key and verifier key. So at this point, for example, when we use Snark.js, we give the arithmetization to Snark.js, and Snark.js, you can use Snark.js to create the prover key and verifier key. And when you want to create a proof, you can also use Snark.js. Well, you can use noname to produce the witness and give that to Snark.js, and they will create a proof. If you're using Kimchi, we actually have code in Kimchi to create proofs and verify proofs and so on, and create prover and verifier key. Technically, we could do it for R1CS, for example, if we used ArcWorks R1CS. I think that would be a good PR. So if you want to like take the output of R1CS and just give it to ArcWorks, that would be interesting. But yeah. All right, so I set a breakpoint here in my circuit writer. I could have done it earlier, but I think this is the more interesting part. So let's try and debug through that. The way I do it, I just go to the examples usually, and I just run one of these examples. This is the arithmetic example, so we can see how it's pretty simple example. So we can see how that, again, it's this example, so you can see how things work. Okay, so let's run it. Oh no, let's not run it. Let's debug it. Let's debug it. And oh, Yeah, let's not care about that. Okay, add another breakpoint. So we're in generate circuit at this point. We have our type checker. I guess we could look at it. I don't know if this is really the output of all of the compilation. Again, this is the output of the type checker, but the type checker has taken its input from somewhere else, like I was explaining earlier. And now you can see that everything is pretty well organized. You have everything you want to know about functions, everything you want to know about structs, everything you want to know about constants. I don't remember what node types are. I think this is something we need to get rid of. And if you look at the functions, you should see the main function somewhere. Actually, let me pull up the example. We have no structs here. So a struct should be of size 0. We have no constants, size 0. Again, constants are things that looks like this. We don't have them here, so size 0. And the function, I don't know why we have 4 of them. Okay, let's look at them. We have Poseidon. Okay, so the way things work is that at some point, anything that's a built-in, we sort of anything that's a built-in, we feed at some point. So here, I don't know why there's Poseidon. That's probably a bug. I don't think that should be here. But assert is these kind of functions are built-ins, and so we want to make them available, and so they're here. There's assert. Oh, the main function is here, of course, and there should be assert equal. Yeah, assert equal. But yeah, Poseidon shouldn't be here. If you want to create a PR to remove that, or an issue, that would be a good issue. So literals are basically, I think we treat them as like, literals here would mean like a number, and like if you write something like that, and maybe actually, just to answer your question on literals, can we run this program? Oh yeah, I guess this should be 2. So things work, right? Literals work in that sense. And what do they look like? What am I doing? What do they look like? We can look at functions. There's, where's main? Main is here. Whoop. It's a function with a body signature and a body. Let's look at the body. What is this? Kind mutable. Okay, what's the kind? We have, where's the kind? I don't know how to check what kind it is. Well, let's just step through it, I guess. So let's look at what this thing does. So we're creating a new circuit writer. We don't care about that. This is the notion of path. Our main function is local. So we're creating this fully qualified local thing. Basically, if you're not local, you're a library. And if you're a library, this means that we cut you from GitHub. So you have a user and a repo, like this. But that's not the most interesting thing. Main info is basically every time you see info, it's something that comes from the type checker. So we're getting that. And we don't want, yeah, we're doing stuff. Okay, it doesn't matter. Init circuit for R1CS, I think it creates the first witness variable as like 1. I don't think it does much more. We don't care about that. Okay, so now we're getting to interesting things. here we're creating the output first. I think the only reason why we create the output first is that Circum does that. So we match the behavior, but there's no reason to create the public output first. We call the add public output function. Let's look at it. Oh, well, I passed it too late. And yeah, we only support an output that's a type field for now. But there's no reason not to support other things. Then we handle all of the public inputs. So we go through the function arguments, and we get anything that's a public argument that has that public keyword here. And what do we do? If it has the if it has the public attributes, well, I guess this one didn't have. Oh no, if it doesn't have it, okay, we have an error. That makes sense. And how do we handle this thing? We can look at it. Basically, we're trying to get the length of that type. Like this is just going to be a field, so it's going to be easy. The length is going to be 1, right? And then we are calling handle inputs. Actually, let me go back to. We're calling basically this is the backend. Oh no, this is not the backend yet. We call this function add public input or add private input for the public inputs, but if you really want to see what it looks like, it eventually calls the backend. So we just figure out how many field variable these are, and then for all of these we call the backend, and the backend will give us this opaque variable. So okay, that's not a very satisfying explanation, but basically you have variables on two sides of the fence. You have variables that are like noname variables. You know, you have a variable for XX and YY. These can be fields, or these can be structs, or like arrays, or these kind of things. So we track these variables on the, let's say, the front end side as objects that are made of smaller variables, and these smaller variables are basically backend variables. And when I was saying earlier, backend is this is something that implements these traits and that exposes this variable thing that's opaque to the front end. And this can be anything. Well, yeah, let's keep it at that for now. Let's go back. Oh no, I went back too far. Okay. Let's can just do rerun task, but it doesn't work. So okay, so we're in this again. We're in this generate circuit stuff. What I want to get is to the compilation of the main function, because I think that's what's interesting. So you can see all of these things as like setting up stuff, you know, processing the public output and the public inputs and the private inputs, all the arguments and return value of that main function. And then we want to get to the meat of it, right? So where's the meat of it? Actually, let me just set a breakpoint. So here we compile the function. Compile main function, right? So let's get into that. We have a question here. The Schnorr, how is it easy to construct Schnorr? I don't know. As I said before, we have a lot of missing features. Like we're really a work in progress language. I think we have a lot of the basics, but we miss like gadgets and things to make. We don't have a good standard library and these kind of things. So what I would say is, if you want to, like, if you're interested in that, just write the code that you wish would compile with noname, post it as an issue, and then we can basically, if you have the code here, we can just debug it, step through it, and see where things don't work. And we can sort of gradually implement the missing features until the code compiles. So I think to write Schnorr would be hard today. We don't have a, yeah, we can't base, Yeah, I mean, I'm not sure where things would break, but let's just assume it'd be hard. All right, let's get into this compilement function. Assert that the function is main, okay, whatever. And then I guess we're past 10, but if people are still watching, I'm happy to continue. I guess I'll keep going for a bit more. So we're in the main function, and this is basically a block. So we're just going to compile the block. And maybe the block is going to return something. If we return something, here we don't return anything, but it could be an example like that where we return a field element. So we would have a return thing here. So that block would return something, and we would have something here. This is not the case. So let's just go back to our example here. Let's get into that. And now we're going through a series of statements. That's what a function is. It's just a series of statements. A statement is basically whatever comes before a semicolon. Every time we enter a block like this, or we could have even this inside a block if we wanted. It's called block. We create a function environment. And this is to make sure that things are well scoped. So here, if we create this XX in this block, then we wouldn't have access to the XS here outside of the block. So very much like Rust or similar languages. So anyway, this is what this f and env, nest and pop really does. Yeah. And then let's go into the first statement. The first statement, again, I was looking at the kind, but I couldn't see it. I guess we'll see what kind it is in the match. We have a compile statement function, and then it matches on it. So what is it? We'll see, and this is how you go through an AST, right? You always have these big ass match statements, and I guess the first one is an assign, so we didn't go very far. But let's see what it assigns here. What's the right hand side? The right hand side is an expression. Everything's always an expression, basically. And we're gonna compute that expression to figure out what it is. Okay, so an AST is a big ass tree, so we have to do that. And no, I don't know why it went all the way down here, but what is going on? What is going on? Oh, all right. I didn't see what it was, but it's too late now. But let's try and imagine what it could have been. It's not a function call. It's not a field access. It's not a method call. Like, we're trying to figure out what this is, right? Right. Okay, let me just set a breakpoint. Fuck it. All right, we're here. It's a binary up. Oh, we're not even here yet. Like, we looked at the right hand side. The right hand side of the assignment is this whole thing, right? So we're looking at what's the right hand side, and the right hand side of this whole thing, of the right hand side. Okay, I'll say that again. We're looking at these assignments. We're looking at the right hand side of this assignment. It's a binary operation. It's an addition. And now we're looking at the right hand side of that binary operation, which is also an expression. They're all expressions inside of expressions. Okay, and we're interested in the. So step out. We're interested in this one. It's a lot of recursion, which is not great. But why does it go down so far? It's a big int. So this is how we treat literals. So this is what it understands to us. It understands it as a big int. And it's just going to, try and parse it and tries to see if it fits into a field element. If it doesn't fit into a field element, you get an error. So that's basically how that works. And you can see then it looks at the op, it tries to see what kind of thing it is. And here it will be an addition, obviously. And if it's an addition, okay, let's look at what it does for an addition. Actually, this is interesting. Okay, I'll set a breakpoint just to make sure that it's taken. Nope. Okay, so what happens during an addition? So that's also a pattern that you will see throughout noname. So maybe it's interesting to talk about it now. But every time you do stuff in noname, it's important to figure out if you're doing stuff between variables that could have different values at runtime when you're trying to prove, or if you're trying to do things with constants. And if you're trying to do things with constants, let's say you have, this thing here, it doesn't make sense to create constraints for these things. Like what you can do is just compute it on the spot when you're compiling, and if you have like thing here, and just replace this thing here with 8, and basically try and reduce all of these constants to things that will produce constraints instead of producing constraints for nothing. I believe this is called constant folding if you're talking about this in the context of optimization in compilers. So this is why you have this match statement here. I'll go back to that. This is why you have this match statement here. You have to figure out if you're dealing with constants. If you're dealing with two constants, in this case, you just do the addition right away. If you're dealing with a constant and a variable, there might be some stuff you can do. If you're dealing with two variables, then you just call the add function on the backend. And it's on the backend to, Plonk will do something different. R1CS will do something different. So we don't know what the backend is doing at this point. But we can look at it if we want. So we'll basically call add constant, right? If this is correct. Shit. Well, let's look at the multiplication, I guess. If I fail to, oh no, okay, I'm here. So what happened in add constant? Okay, so now we're really at the lowest layer of noname. Now we're looking at the backend. We're really looking at how R1CS constraints gets created. So here, what happens? We create a linear combination of the constants. We always like propagating these spans, right? These spans are just for debugging purposes. We're creating a linear combination out of this constant. What is a linear combination? A linear combination is a linear combination. But what else? A linear combination is a linear combination of variables, of like witness variables. This is how R1CS works. I don't want to get into the details if you don't know R1CS, but the way you represent constraints is that you take linear combination of witness variable. So we create a linear combination. Okay, it doesn't matter. What matters is that we add X, which is a linear combination, to another linear combination, which represents the constant 2. So here we want to add 2 linear combinations. I don't know. That's what the backend is doing. And you can look at it, the add function, and basically it does exactly what you expect it to do if you look at your linear combination type, which is just a constant and a list of coefficients and variables. So if you have like, 3 plus 5 times variable 1 plus 7 times variable 2, then the 3 will be here. And here you will have a hash map of V1 to 5. Oh, yeah. So hopefully that makes sense. These are just linear combinations. And what's interesting here is, where are we? What's interesting here is that you're just creating a linear combination. You're not creating any constraints. And this is because of what I explained earlier. In the R1CS backend, we have this sort of optimization where we try to defer things as much as we can. and not create constraints too early when we don't need to create a constraint. So here, this thing doesn't create a constraint. It's only when we're going to reach the multiplication, which is kind of annoying to optimize, that we're going to create a constraint, or if we reach an assert function that we're going to create a constraint. So let's try to step up until this line so we can see how the constraint is created here. All right, so let's get out of here. Yeah, does that make sense? Is this interesting to people? Should I look at something else? I'm going back all the way up until my statement here, right? Because I want to go to the next statement. What is happening here? I guess a statement can return a value if it's a return. If you have like a return statement. So I think that's what we're doing here. Yeah, I believe there might be a bug here if we don't make sure that the return is at the end, but that comment says that we already do that in the type checker, but maybe it would be good to make sure that asserts. I don't know, that we're at the last statement here. All right, sounds like no questions on that. So I guess let's go to the next statement. Okay, the next statement should be the multiplication. Again, I cannot see what's going on, but wait, left-hand side is YY. That's weird. All right, let's go into it. I'm not sure what's going on here. It's an assign. Oh, okay. Left-hand side is YY, because yeah, that's the left-hand side. I keep looking at that as the left-hand side, but that's the left-hand side of an assign statement. And okay, let's try and get to the right-hand side, which has the multiplication. Yeah, so here we compute this expression so that we can do something with it. So let's go again. I don't know why it does this, where it jumps straight into the. All right. So we're here. We have binary operation. That's the multiplication. Left-hand side, we don't. Oh no. Okay. We don't care about resolving these expressions. I'm just gonna skip that. What do we do here? We have a multiplication. We're gonna call fill null. Okay, let's go into this. No. Okay, we're in fill mode. So exciting. We're gonna create a constraint. So these should not be constant, right? Yeah, they're two cells. So we call the backend the multiplication function of the backend, sure. What does the multiplication does? Okay, there's another function. This is what really happens. We have an operation here, a multiplication. So we're going to create a variable to hold the content of the results. So res is a new internal var. What is new? What is new internal var? Oh. What? Okay, what is new internal var? Basically, we're creating what we call a cell var, and a cell var is something in the witness. If you see the witness as a vector filled with cells, that's why we call it cell var. A cell is just like one entry in the vector. And it's a symbolic entry, because at this point we don't have a real value for that. And so the witness vector is this thing in our state. This is the state of the backend when we're compiling things. And this witness thing is just going to increase in size as we. Oh, I'm looking at the wrong camera. It's just going to increase in size as we add these variables. And you can see here we add the constraints. So the index of that variable is just going to be the, in the beginning 0. The next time you create a variable, it's 1. Basically, a variable is just assign an index, which is its index in the table. And then we insert that symbolic variable in the table. All right. And then we just return it as a linear combination because everything's easier because we create constraints. You'll see we create them with linear combinations. Okay. Oh, shit. I think I skipped. But basically, this enforce constraint is called. And what it does is that it takes 3 linear combinations. So here we're going to have a linear combination for private inputs. Other is public inputs. And Y is the rest here, is the third one. Because if you know how R1CS works, it's like A times B equals C. So that's literally what we're going to constrain. And you can see that we're just creating constraints with A, B, and C. You cannot see their values because here we're compiling. And so they don't have values yet. These are like symbolic variables that haven't taken values yet. If you want to debug at runtime with actual values, it's actually something that we want to have that we don't have yet, but we want you to be able to write like debug, or Sericom has something like log. We want you to be able to write something like that so that you can see at runtime with actual values for these things what XX is taking. We don't have that function yet. I think we have an issue on that. If you're interested in taking it, it's not the most annoying thing to write, but you have to add this debug function, or let's call it debug. I don't know how we can call it. You have to add that as a new keyword in the parser. It's sort of it would be sort of a task that touches different places in the code base. And so maybe it could be a task that's like split into like multiple tasks. And one of the things would just be to introduce that keyword. And this thing would panic at first, and then we can implement it. That would be another task. If people are interested, this would be interesting to have contributors look at that. But for now, we cannot. Actually, when I wrote that Sudoku example and I had to debug it, it was a nightmare because I didn't have access to that debug function. So I presume that when we're gonna want to write like more complicated circuits, we're really gonna need that debug function. But yeah. So anyway, I'm not sure what else I could be talking about here. I've sort of showed how we parse things, how we compute these things, how we call the backend to actually do this multiplication, and you can see the assert equal will be the same. Like it's gonna be straightforward actually. Yeah, the assert equal is just gonna be. This is an expression. You can look at it, and the expression is a function call, and the function is gonna be assert equal. Can I see that? Assert eq. All right. It's written here. The function name. It's not main. And you can see. I mean, you can sort of step through it by yourself if you're interested, but you can see that it will qualify this thing as a local function because there's nothing in front of it, so it will presume it's local. Then it will try to get from self, which is the state of the compiler. It will try to get the function info for that function. We can I don't know. We can look into it. Where qualified is I guess at some point it understood that it was part of the std built-ins, which is a spatial library. We can look at it. Oh yeah. I mean, it's not, okay, maybe it's not super interesting to look at it, but it's gonna just return the function info. And that should tell you how to transform that into a circuit. So what happens with the function info? It should call that at some point. It's gonna, of course, before calling it, you want to process the arguments. But yeah, we can look here. That it's going to be a built-in function. And so built-in function has, instead of something that you can compile, and that's like another AST, it has a direct callback. And a callback for assert equal, maybe that's interesting as well. How is assert equal implemented? You can see, we'll check if things are literals. And if they're not literals, it will eventually call the backend, right? It should call the backend. Or constants. Yeah, and here it calls the backend. And the backend has this assert equal var. And if you know R1CS, you can sort of guess what this looks like. It just constrains A times B. A times 1 equals B, right? Or 1 times A. 1 times XX equals YY. That's what it does. With 1 just being that 1. Can you talk about how the equal cells function work? Well, I guess I just did. Does that answer your question? So I think I'm gonna stop here. What I can say is that if you're interested in contributing, I would really encourage you to. I think there's a contributing file there. There's a book, as I mentioned. Actually, let me share the repo again. Yeah, so yeah, you can go to the ZK Security noname repo. There's the book that I mentioned here several times. That I would say you don't necessarily have to read it, but if there's something kind of confusing, if you go through the internals, you can sort of see if we already explained these things. Otherwise, it's fine to post an issue and we can spend some time to explain it. We have a bunch of issues with different tags, and you can look at all the easy issues if you want, and these are good starting points to contribute. As I said, there's a lot of low-hanging fruits that might be interesting to tackle. So maybe these tasks don't have the best description, so it's also fine to write a message, and we can write more and explain more what's going on. And yeah, no, we have a Telegram. We have a Telegram chat. Maybe someone can post the link to that Telegram chat in the. Actually, if there's only me who can do that, so I'll do that. Or actually, everybody should have the link. But anyway, I'll post it just in case. There's a Telegram chat where you can ask your questions there. We're happy to help. And yeah, I'd say we're excited to see noname being more and more useful. I think for that to be the case, there's still a lot of functions and missing features. And the best, I'll say this one last time, but the best thing I think we can do is basically write code that we wish would compile. And if it doesn't compile, make sure that we can make it compile. So yeah, writing code that doesn't compile but that should compile is a good first issue. Yeah, thanks for joining the stream and listening to me talk for an hour and a half about noname. I'll just stay here for a few minutes just to see if anybody has questions, but you're allowed to leave the stream at this point. All right. Sounds like there's no questions. We're on Telegram anyway. So yeah, feel free to ask questions there. And oh, how long have you been building noname? Yeah, I guess it was kind of a side projects from where I was working at O1 Labs on Kimchi and Mina, and the project sort of it came because like I was looking at a lot of very low level constructions, and it was kind of a like these low level languages are kind of annoying to use, and not it's hard to not write bugs when you use like something like Circom, and so I sort of put that aside for a while. Like we didn't really work on the name for some time, and then I saw that nobody was really filling the void of what noname could be, and so we basically tried to restart the project again, and we Kata and I started working again on this I guess a month ago or 2 months ago, and we made it work for R1CS, and we got really hyped about I think the road to making it very useful is pretty short. I think in a few months we could make it so that it's actually quite compelling to use. And so yeah, it's been a while, but I think development has picked up again in recent months. All right, I'll end the stream. Thank you all again. Hope that this brings some contributions and that people get excited about noname. Yeah, see you at the next session like that. If people want another one, I'd be happy to stream again. All right, cheers.